Good morning. Welcome to Krishna's classroom. We continue with our exploration of the concept of uniform convergence and the Vitali convergence theorem. In fact, we proved the Vitali convergence theorem last time. Now let us recall this, because eventually our objective of this talk is to get a more general version of it. So let us recall this, the statement of the theorem. Let Vitali convergence theorem. Let E be a finite measurable space. Suppose sequence Fn of functions be uniformly integrable over if the sequence Fn converges to F pointwise almost everywhere, then F is integrable over U, and limit n tending to infinity This is the statement of the theorem. So what are the things that we assume? First of all, we assume that E is a finite measurable space. So the finiteness is one condition that we assume. Then we talk about a sequence of functions defined on E. We assume that this is uniformly integrable over E. So uniform integrability is something that we assume. The consequence is that if Fn converges pointwise to F, then this last statement holds, which amounts to saying that the integration and the limiting process can be interchanged. This is yet another theorem in this class, under what conditions the limiting process and integration can be interchanged. Now this is the question that you are asking. Okay. Now in this, the assumption that E is of finite measure is something which probably is too much of a restriction. We will explore that, and that eventually leads to the general Vitali theorem that we shall do. At the same time, uniform integrability is an ingredient in supporting the interchange of integration. Now, to highlight this particular aspect, that is the uniform integrability, so we make a remark. The uniform integrability is an essential ingredient to support the interchange of the limiting process and integration. Now, in this regard, we shall prove another result which will highlight this particular aspect. So, let me take it up. So, the next theorem let E be of finite measure. Finite measure. Suppose Hn is a sequence of non-negative integrable functions which converges to H identically equal to 0. Then limit equal to 0 if and only if uniformly integrable. So, what we want to say is that if the interchange of limit and the integration is assumed, takes place, then that would imply that the Hn is uniformly integrable. So, that is the sort of relationship that you have. So, E is something with a finite measure, Hn is a sequence of non-negative functions which converge to 0 pointwise, on E, and then the limit of the integration and that is the limiting process and the integration can be interchanged provided Hn is uniformly integrable. So let us explore this. One part we have already, it is merely the Vitali convergence here. Okay. So let us explore this. And what is significant is the second part, the converse of it, which highlights the significance of the uniform integrability. So, when you look at the proof of this, assume uniformly integrable. Then what you have is this limit n tending to infinity zero. Because here we are assuming Hn converges to so this is merely the Vitali convergence here. The sequence H. Okay. So that is one part. But what is significant is the converse of this. Okay. Conversely, assume limit n tending to infinity so we are assuming Hn is non-negative. Okay. So note that zero. So let epsilon positive be. Then there exists an n depending on epsilon such that from this limiting process such that integral over E Hn is less than epsilon for every n greater than or equal to epsilon. So that is a consequence of this relation. Now what we want to prove is this. So we claim that it's our claim. This is our claim. Now you see, you look at these functions. This is a finite collection, and E is such that measure of E is finite. Hence, by default, uniformly integrable. Because this we have proved that if you have a finite collection, then that is always uniformly. Okay. Therefore, you see that if delta is a number corresponding to epsilon, if epsilon positive, then what you have is this: for any with measure of A is less than delta, integral over A of Fk is less than epsilon for K equal to n minus. Further, with less than delta, integral over A of Hn is less than or equal to integral over E of Hn, which is less than epsilon for every n greater than or equal to. Okay. So combine these two. So combining these two, we get the uniform integrability of this. So together, every measurable that is Hn is uniformly integrable. So what this result highlights is that the uniform integrability is an essential ingredient in making this conclusion. That is the interchange of integrability and limiting process. The interchange of limiting process and the integration. Okay. Now we ask the following question. So we ask the following question. Is condition measure of E finite for the validity of the Vitali So this is the question that we are going to take up in the remaining part of this lecture. Let us explore this. But before we try to explore this, we will show that it cannot be simply dispensed with altogether, or if we want to dispense with this finiteness assumption, then possibly we need some extra conditions to do it. Okay? So we will explore this. So let us explore this more. So we will look at some examples. That is the natural. First example. Let us take E to be suddenly measure of E is not finite. The Lebesgue measure of E infinite. That is, it is not finite. So certainly the condition of the Vitali's theorem that we have proved is not satisfied. Now let us look at the following example. So let us take En that's the notation. En you define this. Now let us define the functions. Fn, sequence Fn is the characteristic function of, that means on En the function is equal to 1 and elsewhere it is equal to 0. Okay. So this is what you have. You have so rather like one. And so what this is 1. So the graph of the function Fn is 0 everywhere here and outside, and on this set it is equal to. So you have a sequence of functions of this kind. Okay. Now you see that Fn pointwise 0 that's quite easy to see because the tail of the sequence is always equal to 0. Now the question that you ask is this. Suppose you take limit n tending to infinity. Now you see that this is equal to 1 because essentially it reduces to integration over n to n plus 1 where it is equal to 1, and therefore this integral is equal to 1, and this is not equal to 0, which is the limit of so this shows that, so this example shows that as such it is not a limitation we have just got on the theorem in the Vitali convergence theorem. Okay, that means there are examples where if you do not assume, then the result is not valid. Well, that's a very illustrating example. Then of course you cannot, so that this example makes it clear that, so what we can assume, what we can infer is that measure of E infinity, the Vitali convergence theorem as such, the conclusion of the Vitali convergence theorem may not be. That's the inference. So the natural question that you ask is, suppose you put in some extra conditions apart from the, when you relax this condition that measure of E is infinity, suppose you put in some extra condition on the collection of functions that you choose, can you get this Vitali convergence theorem to be true? Okay. So that is the way in which we explore the problem. So the statement, the problem that we look at is this: is the Vitali convergence theorem, is it possible to have the conclusion of the Vitali convergence theorem to be true with some further restrictions on sequence Fn when this is the question that we are asking. So without assuming anything, you cannot do it. It's not purely a limitation in the proof of the Vitali convergence theorem for the case measure of E is equal to is finite. Okay, it's not purely that, because you have an example where it doesn't work. Now let us look at another example. This is a modification of this example 1. So we take E to be equal to again 0 infinity. Measure of E is infinity. We define En you take as n plus 1 by. Okay. And Fn you define as chi for n equal to in this this case, what happens? Then you see that once again pointers. And now let us look at what happens to the integral. Now you see that these functions the collection of functions is uniformly integrable. Obviously, is uniformly. Therefore, all the conditions of the Vitali convergence theorem is satisfied except that it's finite. Except that the E has finite measure. That's something that you know. Right. Therefore, I mean, this is easy to verify. Now you see that you look at this one, limit. Again, once again, the question that you are asking is, can you interchange the limit and the integration process? What is this? This one is the integration of 1 over the interval n to n plus 1 by n. And that's equal to 1 by n. Which is equal to 0, and that's equal to integral over E. Yeah. So which is same as integral over E. So interchange of the integration and limiting process is valid in this particular example, although the domain of the functions is not a finite measure. So remark, the interchange of limit and integration is valid although so there are situations where the interchange of limit and integration go through. Okay. So what makes it do? I mean, this is the question that you are asking. So we will explore this a bit. So what we need is, what we are is integral over E of Fn minus integral over E F can be made arbitrarily small by choosing n sufficiently large. So the approach appeared to be the following. Somehow or other you reduce the problem to the possibility of applying Vitali's convergence theorem with measure of E finite. Okay, so let us explore this. How do we explore this? Okay. So we try to find a measurable subset E naught of finite measure such that integral over less than epsilon can be made as small as this. So this is a crude way of getting resolved. Okay, that is, more precisely, given epsilon positive, we would like to find a measurable subset of finite measure such that integral over f on the complement of E naught if that is possible, okay, then there is a way out, because then all that you need is manage the whole of Fn so that somehow we are able to get this situation, that is for everything. Suppose we are able to get this. Okay. Then of course what we want is this difference to be manageable. So you will split this into two portions. Okay. What we do is this. Okay, and show that this is somehow small. Okay, so if you can make this part arbitrarily small, okay, then this part is a question of managing it on E naught, where E naught has finite measure, and there you can apply Vitali convergence theorem. Okay, right? So this will be the strategy, right? So okay, this is what we look forward to. We can apply the same technique as in the proof of the Vitali convergence theorem to manage on the set E naught of measure of finite measure. On the rest of it, if you could somehow get this arbitrarily small, then it is done. Okay, so that will be our strategy. Okay, let us see how we work on this. And that is exactly what happened in that second example. You see that, if you take the interval, take the special case, in that example what we could do is this. See, the second example was we had Fn equal to this was the sort of functions that we had. Okay, then we found that mod Fn can be made as small as you please by choosing sufficiently large. Because what is this integral? Sorry, not mod Fn, integral Fn can be made small by choosing n sufficiently large, because integral Fn 1 by n, and this goes to 0. Therefore, it is manageable. That part is manageable. So we are going to explore this kind of condition. So we introduce an extra condition on the functions fn other than what you call uniform integrable. Now this is what is called tightness. Okay? So we introduce a condition, an additional condition, that is a condition other than what is called uniform integrability on the class of functions that we choose. This is what is known as tightness, and to take care of this kind of scenario. Okay. So we will okay. So before that, we just make the following observation. Let over E. Then for every epsilon positive, there exists a set of finite measure V naught contained in for which integral E for any function f that is integrable over E, this condition is satisfied. This is a very simple result. Let epsilon positive be given. The non-negative function mod f is assumed to be integrable. Is assumed and measure of E now, by the definition of integrability, of the integrability of mod f. This is non-negative. There exists a bounded measurable function G defined on E such that which vanishes outside a set E naught of finite measure for which and over we are taking the non-negative less than. That means it can be approximated by a function g, a measurable function g on E which vanishes outside a subset E naught of E of finite measure. Okay. That means essentially this function g is defined on a set of finite measure. This property. Therefore, by linearity, and additivity, over disjoint domains, we get the following result. We have the following result, namely integral over G, and this is 0. Yeah, this can be written like this because it is 0 on this E slash E naught. Okay. Therefore, this is equal to, this is of course less than or equal to integral over E mod f minus G, and this of course is less than. Okay. So you get integral over E slash E naught less than epsilon. That's what we wanted to calculate, right? So we will just, so we have got this result that there exists the existence of such a set of finite measure E naught such that on the complement of it, this mod f can be, the integral of mod f can be made as small as p. Okay, so corresponding to epsilon, you have a choice of. Now we shall use this idea. Well, if you look at that a second example that we have looked at, this kind of scenario is emerging. Okay, because what happens is that outside a, you take E to be, E naught to be 0 to capital N, and outside that you see the integral of mod f is going to be less than 1 by n. So given epsilon, you choose n sufficiently large. So associated with that n, you have this. For example, in 1 upon n is less than epsilon. Okay. Then E naught intersection zero to n. And in that case, you see that which implies integral over E slash E naught of therefore its limit also becomes valid for which it is valid. This is the scenario that you. Okay. So that completes the proof of this theorem. Now that leads to the concept of what is called tightness. So we introduce a new concept. This is just to enable us to talk about second relation. This is the terms that we use. A family F of measurable functions on E is said to be tight over E if given epsilon there exists a subset of finite measure such that integral over complement of E naught in E of so this is what you call the concept of tightness. Therefore, what we hope to do is the following. Apart from the uniform integrability of Fn, we also assume that this collection is tight over E. Okay? Then we can, take out a subset E naught of finite measure from E, and on the complement of which each Fn has its integral as small as we please. We can choose such finitely measurable subsets corresponding to each epsilon. Now this is the advantage. Okay, so that on the finitely measurable, so when you talk about the integral of over E of Fn, okay, we can split it into two portions. One on this portion and the other one on E naught and the other on E slash E naught. On E slash E naught, it is manageable because of the tightness condition. On the other portion, it's a set of finite measure where your original Vitali convergence theorem can be applied. And then put these two things together, we hope that we can arrive at the conclusion of the Vitali convergence theorem, namely that the interchange of limiting process and integration is valid. Okay, so with these remarks, let me just conclude today's talk. Sorry for that small interruption that happened in between. I hope I'll get that expunged while uploading the talk. Thank you very much.